Hello and welcome back. Okay, so I've been doing a whole bunch of work that you won't have seen much evidence of yet. So I've been working on the assembler, and I've also been working on a number of different PCBs that will hopefully show up at some point, if I haven't got around to finishing them and sending them off for manufacture yet. But today I want to talk about programming. So a lot of the recent programming exercises I've done have been testing new functionality out, and we've pretty much been seeing what was going on just by the register LED statuses. And I've not done anything with the LCD display, but in the last video I added function calls, and so we should now be able to start building up a library of functions that make life easier for us as a way of amplifying up the kinds of functionality we can implement easily. And so I'd like to write some code for driving the LCD display as a little library of functions, so then we can make easier use for that in the future. I think what I'm going to start off with is the Fibonacci sequence that we ran before, but we're going to make it output to the LCD display. Okay, so this is basic code of the type we've done before. I've got the reference to the architecture definition. The .export directive defines how much data we're going to output into the ROM, so address 0 through to 32767 is the data we want to save, so that's the size of our ROM chip, and right now basically nothing. I'm immediately going to reference the two main new features I've added. So .include directive, which is basically going to pull in display.inc as if it was included here. I'm also going to use this directive .segment. Segment selection is going to be very useful for managing where data goes. Now the idea is we can name segments instead of the instruction sequence or declaration sequence in the assembler file being one after another in memory. They're one after another in the current segment, so I can have a segment I declare as my code, and I can have a segment that I declare as my read-write data, which I can stick in a different location in memory, i.e. above 32K where the RAM is, and I can also have a read-only data section which is going to be positioned at an address in the ROM. So display.inc is currently empty, apart from I've got a .segment libcode. Now this is going to be the same as the regular code, but I will implicitly have this positioned behind the code segment, which the one rule I've got about segments in the assembler is code is first. I could use a .org directive to position it at a specific location, but a feature I've built into the assembler is that if I don't specify a location, it will stick it immediately after the previous segment. So Fibonacci sequence, that is f at x is equal to f at x minus 1. First we need to get the display set up. I'm going to load the address of a function we're going to call display init and call it. I'm going to take the implementation code for that from the original Hello World we wrote. And now I want to write a function for writing a string to the display. This is one thing I want to add to the assembler next, is some way of adding local labels that are only referenced nearby, just so I don't need to worry about prefixing all of my labels. Okay, so I'm loading the character in. Let's check if it's a 0. If so, we jump to tx, which is the end of the loop. Otherwise we write it out and do an unconditional jump back to the start of the loop. See if that assembles. It's going to take some getting used to. Okay, I'm going to have to update this output log at some point. can see up here that the initial code at the entry point is first. Yeah, so down at address 0. Then we have the display library, and then we have our data RO section after that. But it's outputting it in different order here, but the addresses are correct. I do plan on adding a break or halt instruction at some point, but I haven't done that yet. Okay, this has changed around a little bit. I've turned the display module around so I can add a little camera facing down at it and get positioning on that, so I can hopefully display the outputs on the screen a little better. Let's just be bold and run it. Excellent, that's done exactly what we hoped. Okay, how are we going to do this? Okay, so it sets everything to 0, but actually, if we say A and B are the current value, these are going to kind of alternate between this pair and this one. Print out AB, and we haven't worked out how we're doing that yet. Then we want to roll it on. We need to save off A and B. So do a 16-bit add of CD to AB, and we can restore those values. So if the carry flag is set, that last add has overflowed, so we're gone beyond what we can fit in a 16-bit value. So we'll jump to the end. If not, we'll load up the loop variable. Okay, so A, B, C, and D are important variables here that we don't want to overwrite. But this will actually compute the entire Fibonacci sequence and finish. So now we need to think about how we're going to display it. So I would like to say that sufficient number of times. So that will display first a little bit. Now we need to think about how we're going to keep count of these. I know, let's just use one of our counter registers. If we increment DI with each step, we don't have any spare general purpose registers here without saving them off. We know this function overwrites A. So let's push A. And we want to get the current value of DI, somewhere we can work on it. There should be a lot less than 256 Fibonacci numbers in this range, so we just need to use an 8-bit value. So I want to put stubs in for an 8 and a 16-bit, right? Now we're going to do this in hexadecimal because that's the easiest way of doing it for now. I'm going to add a function for a 4-bit version as well. Right, don't know what any of these functions do yet. I'm just going to output that equals sign directly. Be overkill to create a string for it. Now we need to restore the version of A we saved off. Okay, now I want to look at these write hex routines. Please be careful about preserving the correct registers. Display write 16 hex passes its value in A and B. I think it's going to be convenient to us if these don't overwrite any registers. Although I think most functions are going to modify TL and TH at minimum, so let's say that. Okay, so A and B, now we're definitely going to need to change these around a little bit. But if we think about a 16-bit hex value, right, so here's our 16 bits and we want to display them from right to left. And the reason why hex is used quite widely is this is actually quite straightforward. So 1 digit of hex translates to 4 bits. 1 byte of hex is 2 digits. We can implement this write 16 hex by making 2 calls to write 8 hex. So the first thing we need to do is preserve the return address. I want to preserve A, because we will overwrite it. So the high byte is what we want to output first, so that's going to be contained in B. So copy B into A, and then call display write 8 hex. Then we can recall the original value of A, call it again. This function may have overwritten tx, so we need to load it again, but that will output the lower 8 bits, and then we can return. Job done. Now we need to implement the outputting of an 8-bit value. Once again, we need to preserve the return address. So we want to save B because we're going to use that as working data. And the value we want is in the top 4 bits of A. So we shift that right by 4 times, and we have it. And then call our function that displays a single digit. Actually, I don't see why that one's going to not preserve tx. We'll avoid the extra load. I'm going to load A with 0f, and then A with B, which extracts the bottom 4 bits. Call again, restore and return. So what we're doing at the moment is called top-down programming, where we define our largest function and then we use a function we haven't written yet to implement it and repeat until we've got a fully operational function. So here, A is a value from 0 to 15. Actually, I will need to edit TL and TH here. I could do this one of 2 ways. A very common method of doing this is to have a lookup table. Then you use the incoming value as an offset into this table to read the character out. Yeah, let's do that. It means we need somewhere to store it. So I'm going to declare a different segment. This is interesting. It would actually be convenient for me to load this directly into general purpose registers. So I'm going to add another macro similar to the load of tx. Okay, so now we need to do a 16-bit add of A, B and CD. Load the appropriate character and output it. Now we need to make sure we've saved and restored everything we need. This is where it gets tricky, because this function doesn't touch C or D. It doesn't actually need to be preserved between these 2 calls. Let's do the save and restore and we'll worry about optimizing it later. Okay, let's give it a go. Okay, that character's not right. Let's run it till the point where it goes wrong. Obviously we don't want the values to be wrapping around the lines like that, but we haven't done anything to stop it yet. Okay, hopefully we've stopped that just before it crosses back. There we go, so there's the return. Okay, I can already see one problem. The value of DI has been corrupted. Yeah, we reference it in the display string routine and we need to preserve it. Okay, So that should be an easy fix. But then that first digit came out wrong. Should be outputting 8 and then 6. That 6 is correct. Okay, I didn't have the correct display selected for recording when I fixed those two issues. What I've done in the display write is I've saved and restored DI by copying it into TX and saving TLTH on the stack and then reversing it at the end. And then the bug here with the character was the shift right was corrupting the upper bits in A because it rotates through the carry flag. We might not have spotted that for a while actually if we hadn't made the earlier error. I've switched this around so that instead of doing the AND by 15, 0F in hex, down here for the lower 4 bits, I moved the AND up into the single digit display routine, and then that just makes it all a little bit neater. So it should actually be 0, 0. We need the equals, and then we should get a 4-digit value, which didn't happen. Let's see if we can catch that. Okay, I'm going to spare you this piece of debugging. I don't explain it very well while I'm working, and I think I'm going to do a short video on this in future because it's quite an interesting issue. Okay, in this case we can fix that trivially like that. In this one I think we're just going to need to add the NOP. Okay, let's see what that does. That's good. Okay, so the next one should be 2. Okay, that looks like a random character we generated from noise on the line, but that's then outputted the correct number. I don't like the fact that we got that random character, but then we haven't actually done the main circuit board upgrade that was designed to nail that issue fully on the head. So now this should be value 04 is equal to 5. So it should be 8. Yeah, so this looks like it's working brilliantly. So now we need to look at how to separate out those lines because that doesn't look very neat right now. Okay, so what I'm going to do is add a new line function. Now, scrolling the display would be ideal. We've got a complexity that the characters on the display aren't in the order we expect them to be. So the third line is second, so 40, then 20, then 60 is the address sequence. And then in an ideal world we would scroll when we get to the bottom and we want to add a new line, but we're not going to be able to do that very easily. We'd be sat there watching it redraw slowly. Might be fine once we're running at a higher clock rate. So I think what I'm going to do is get a line index variable created. So we're going to create a new segment called data read write. And we need to position that explicitly at the start of RAM. Now memory isn't pre-initialized, so we can set it to 0 in the initialize function. Then we create a little lookup table of the addresses into memory or into the display that we need. So we load the current line, we increment it, need a NOP there because A won't have fully loaded by the time it tries to dispatch this instruction. Okay, so if the line ended with A isn't 4, you need to store it back in its location. Okay, so we don't need to worry about updating that value because we're just looking to see if it's 0, and then we want to clear the display again. Display current line has already been put back to 0. Now, clear display will actually put us back, so we can just return there. Whereas here we need to set the right address. AB now contains the address into this table. A is now the display address. Now, how do we set the cursor position? Okay, so we need to output a command with the address and this bit set. The easiest way for us to do that would actually be to add that here. Okay, actually I'm going to take that return out for now. We need to preserve A, B, C and D. Actually we can still do that, we just need to do the pops at the same time. So in theory this should give us a nice neat output. Okay, it looked there like it was dumping all 32K of memory with lots of zeros. So I'm going to need to fix up my assembler to stop it doing that. Now these programs are getting bigger, I need to improve the output. Let's see what this does. It's looking good. This should be 1. Okay, now it should wrap back to the start and clear the screen. Excellent, that's working. I'm going to have to watch this in real time, but you can watch the fast forward. Okay, so there was a couple of pure display glitches there, which I'm hoping that the new backplane PCB should sort out. But all of those numbers checked out. That's brilliant, that worked. Took its time though. Let's see what happens if we change the clock rate. My cheap hack for changing the clock rate is to just remove that capacitor. So that's 17 hex, that's 23. The 23rd Fibonacci number is 46,368, which is indeed B520. So that took a tiny amount of time compared to the first run. Probably similar for you in the fast forward, but yeah, that's very promising that it's stable. Okay, this is the most programming I've done for this system so far, and there's going to be an awful lot more to come. So I would appreciate some feedback on how much coding you want to see. Now the performance of this code isn't too bad. Printing the hexadecimal numbers, it could be done quicker by not breaking it down into multiple layers of function calls. So I may rewrite that at some point, but I won't subject you to it. Now the big deal is I'm outputting hex numbers. And I'm doing that because it's actually pretty easy. You can perform that simple subdivision of the bits, and 4 bits goes to each hexadecimal digit. But what we'd really like to do is be able to output those in decimal. And that's going to take a little bit of extra effort. What we need is a division and a modulus operation, and that's not trivial. Now, we did talk about the kind of effort that would be necessary to add that to the ALU, and that's a bit out of scope for a CPU of this type that's being initially built on breadboards. So we're going to need to write some code, and that's going to be the subject of my next programming video, which I'm going to do as a bit of a deep dive into optimization and getting this stuff done really efficiently. And we'll finish that off with having the Fibonacci sequence outputting in decimal, which should look a lot nicer. I very much hope you found this interesting though. Thanks for watching. Goodbye.